Hi, I'm Fran. You may remember me from such videos as the Vernier energy sensor, the Vernier emission spectrometer, and the Go Direct sensor cart off track. I'm here today to tell you about one of my favorite experiments. This is Galileo's experiment to figure out the acceleration of gravity. And it's figured out by just letting this cart, which is a Go Direct sensor cart, roll down the incline. So how does that give me the acceleration of gravity if gravity is like things falling? Well, Galileo figured this out too, because he did not have a stopwatch. He could not measure the time it took for something to fall. But if you've got something that's going to roll down a track, a frictionless track, then this track has some angle theta. The acceleration of gravity has two components. It has a parallel component and a perpendicular component. We're interested in the parallel component here, and that is going to be equal to the acceleration of gravity times the sine of theta. So what we're going to do is we're going to use the sine of the angle and the accelerations that we measure to get a graph, acceleration versus the sine of the angle, and we should find that, let's see, sine of 90 degrees, 1. We should have 1, this will be g. So that's our goal with this experiment. We're going to be doing some mathematical and computational thinking and some modeling for those of you who do NGSS. So I've measured my track. It's that long, 1.218 meters, and I need to know the height. So what I can do here, I know that the bottom corner is always going to be on the ground, and this is a very exciting ruler that I searched high and low for, where the edge of it is actually 0. And I'm going to measure the bottom of the track at this end. That height difference is going to be the opposite side of my right triangle. This is my hypotenuse, and remembering my trigonometry, the opposite side over the hypotenuse is equal to the sine of the angle. So this height is 0.043 meters. I'm just going to graph velocity versus time with this. And get the slope. So the slope for this is 0.2766. If I were having my students do this, I would have my students do this 3 more times at this angle, change the angle, go 3 more times, change the angle, 3 more times, change the angle. I am not going to do that. I'm going to do my next angle right now using the time-honored physics teacher method of using textbooks for their intended purpose, propping up ramps. The height here is 8.5 centimeters. Collect a new set of data. 0.6105. Let's get another angle here, 14.9 centimeters, 1.101, 19.8 centimeters, I love how collecting data is so quick. If something goes wrong, you can just do it again, super fast. 1.486. Next step, I'm going to have to figure out the sine of the angle. For each of these, that's going to be the height divided by the track length. Time to do some manual entry. I have 4 points on this graph. If I fit them to a straight line, it looks like that will be a nice curve fit on a straight line. But what I'm interested in is what happens when the track is vertical. My cart would be falling. What's the acceleration then? Well, I'm not going to do that. I don't want to break the cart. So I'm going to extrapolate. Linear curve fit. Then I'm going to interpolate. So I know interpolate, different word than extrapolate, means the same thing in this case. There I've got 1. So what is this when I've got a sine of the angle equal to 1? 9.44. So not 9.8. I was hoping for 9.8. It's always nice to do when you do the video to have 9.8. But why isn't it 9.8? I bet you could ask your students why it's not 9.8. Friction! Excuse me. Of course, if you have your students do 3 trials, take the average, and do more than 4 points, they might get closer to 9.8 than I got. Give it a try. Have some fun.